Okay, it is the start of unit number 11, and of course, we're going to study. What are we studying? Circles! We're going to study circles. And for this first lesson, our learning target is going to be the properties of tangents. Let's make sure we know what a circle is, and let's make sure we know what a tangent is. Circle is going to be the set of all points that are the same distance from the center. Right? So there's a picture of a circle with a radius and a center. We call the given point the center of the circle. In this case, this example, center is point A. And then the distance is the length of the radius. In this example, line segment AB is a radius. And there are many different ways I could draw a radius in that circle. But however I draw the radius, it's got to be a line segment. One endpoint must be the center of the circle. The other endpoint must be a point on the circle. Now, for a tangent line is a straight line that touches the circle at exactly one point. It's called the point of tangency. Neat thing about this is if the line is tangent to the circle, it'll be perpendicular to the radius at the point of tangency. Right? So the radius and the tangent line form a right angle. So we've got a nice little theorem here. Right? A line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at that point. So in that picture, you say, hey, we've got line M. It's tangent to circle Q. And the only way that works is if it is perpendicular slope to segment QP. So if it's tangent, we know it's perpendicular. Or if we know it's perpendicular, then we know it's tangent. Now, if we happen to have more than one tangent line, in this case it looks like line segments, where those line segments would be part of tangent lines. Notice that they have to be congruent. Right? There's no way they can be anything other than congruent, which means they would have the same length. Let's take a look at 3 examples. First example is line segment ST tangent to circle P. Well, if they are tangent, I know that angle STP has to be a right angle. And of course, if I've got a right angle on that triangle, I can use the Pythagorean theorem. Now, technically, I'm actually going to do S squared plus P squared equals T squared by the way those angles are labeled. But I'm just going to go with the good old famous ABC deal. So for my A and my B, those are going to be the legs. That's the 12 and the 35. If I square each of those values and add them together, I get 1,369. Is that going to be the same as C squared? Let's find out what happens if we square the hypotenuse. Oh my goodness, if we square the hypotenuse, we get the exact same figure. So yes, line segment ST is tangent to circle P. Right? Because if I try to do A squared plus B squared equals C squared, and I get a true statement, it's got to be a right angle. Second example, this is my personal favorite of the whole bunch. We are being told that point B is a point of tangency. So we know that line segment AB has to be a tangent line segment. So let's find the radius R of circle C. Well, if point B is tangent, we know we've got to have a right angle, so I can use the Pythagorean theorem. A squared plus C squared equals B squared. What on earth is going on here? Oh, look at the diagram. The right angle is labeled B. That means the hypotenuse is lowercase b, right? The legs are A and C. The hypotenuse is B, right? Hey, this is what happens when you steal a picture off the internet, right? So what is A squared? Well, opposite angle A is side A. That's line segment CB, and that's just R. Side C, well, that's line segment AB. That's easy. That's 80 squared. Now the hypotenuse, side B. Well, I see 50 feet, but then I also see the radius. So the total length of segment AC, which is the hypotenuse, will be R plus 50 quantity squared. Well, 80 times 80, that's easy enough. 6,400. A little bit trickier, R plus 50 quantity squared. I need R plus 50 times another R plus 50. So you guessed it, I have to do FOIL. First, R times R is R squared. Outer, R times 50 is 50R. I for inner, 50 times R is 50R. L for last, 50 times 50, 2,500. Let's combine like terms. I'm going to have it appear underneath the circle because I need a little bit more room. Notice 50R plus 50R became 100R. Hey, this is really sweet. I've got an R squared on each side of the equal sign. Let's subtract R squared from each side. That looks a lot more straightforward now. Subtract 2,500 from each side. Finally, divide by 100. R equals 39. And of course, there are labels in the diagram, so I should really say that the radius is 39 feet. Right? I should put the label in there. Ready for the very last example? Again, I say, hey, segment RT will have to be congruent to segment RS. In other words, the length RT is going to have to equal the length RS. So 3x plus 4 has to be 28. Subtract 4. Divide by 3. And there are no units shown, so I'm just going to say x is 8, right? Because they don't tell me if I'm working with feet, inches, or whatever. So, of course, we're going to have a worksheet. And let's see what beautiful, awe-inspiring photograph we're left with this time. Oh, some lovely rocks underneath the water near the shore of a lake. My hunch is this is probably from Glacier National Park. But it could be somewhere else in the Rocky Mountains too, so I better be quiet. I just stole this off the internet somewhere.